Welcome to Math Zone African Motives. Today, we're diving into a powerful integration technique called integration by inspection. By the end of this video, you will be able to first, define integration by inspection. Second, integrate functions of the form f of x to the power of n times f prime of x. And third, integrate functions involving exponential and logarithmic forms. In simpler terms, you'll learn to look at an integral and, with practice, find the answer right away. So, what exactly is integration by inspection? Let's break it down. At its heart, inspection relies on the fundamental relationship between differentiation and integration. We know that integration is simply the reverse process of differentiation. If we can see the derivative of a function inside an integral, we can work backward to find the original function. This method is a shortcut. It's a way to find an antiderivative by carefully examining the function and recognizing a familiar pattern. Instead of going through lengthy calculations, we can predict the original function just by looking. Essentially, if you see an integral and you can spot a function fx and its derivative fx within that integral, you can often apply a standard formula. The first major pattern we need to recognize is the integral of a power of a function multiplied by its derivative. This pattern has a specific formula. The integral of a function fx raised to the power n multiplied by its derivative f prime of x equals the function fx raised to the power of n plus 1, all divided by n plus 1 plus a constant of integration. C. This formula is valid for any real number n, except for n equals -1. Let's highlight the key components. The function we're looking for is f of x raised to a power, and its derivative, f at x, must be present as a factor. Once you identify these, you can apply the formula directly. Let's see this in action with an example. Let's work through the first problem from our sheet. We need to integrate the quantity x squared minus 3 raised to the 9th power times 2x. Our first step is to identify the pattern. Is this in the form of f equals x to the power n times f prime of x? Let's look at the function being raised to the power n. We can see that our function f of x is x squared minus 3. Now, what is the derivative of this function? The derivative of x squared minus 3 is simply 2x. If we differentiate x squared, we get 2x, and the derivative of a constant like -3 is 0. Let's check if our derivative f prime of x is present in the integral. As you can see, 2x is exactly the other part of the integrand. So, we have successfully identified the pattern. So we have fx equals x squared minus 3, n equals 9, and f prime of x equals 2x. We can now apply our standard formula. Now that we've identified the components, let's use the formula. Remember, our formula is the function to the power n plus 1 divided by n plus 1 plus c. We have f of x equals x squared minus 3 and n equals 9. Plugging these into the formula, we get x squared minus 3, all raised to the power of 9 plus 1, and we divide by 9 plus 1. Let's simplify this expression to get our final answer. 9 plus 1 is 10. So the final integral is the quantity x squared minus 3 raised to the 10th power divided by 10 plus the constant of integration, c. And that's it. Comparing our answer with the memo, we can confirm it is correct. Verified using memo. Notice how quick and direct that was. This is the power of integration by inspection. Now, let's explore a very important edge case for our first formula. We said the formula for f of x to the n times f prime of x is not valid when n equals -1. Why is this? Well, if n were 1, the denominator would be n plus 1, which is 0. And division by 0 is undefined. So what do we do in this case? We use a different formula. When n is -1, our integral looks like the integral of f equals prime of x divided by f of x. The formula for this form is the natural logarithm of the absolute value of f of x plus c. Let's break this down. The pattern to look for here is a fraction where the derivative of the function in the denominator is present in the numerator. If you see this, you immediately know the answer is the natural log of the denominator. It's important to include the absolute value bars around fx because the natural logarithm is only defined for positive numbers. Let's apply this new formula to problems 3 and 4. The third problem is the integral of 4 divided by 4x minus 3. The fourth problem is the integral of 1 divided by 4x minus 3. Both of these look like our logarithmic form, f prime of x over f of x. Let's analyze the denominator in both cases. Our function f of x is 4x minus 3. Its derivative, f prime of x, is simply 4. Let's look at problem 3 first. The numerator is 4. This is exactly f prime of x. The denominator is 4x minus 3, which is f of x. So we have the perfect setup, f prime of x over f of x. We can now apply the formula. The integral is the natural log of the absolute value of 4x minus 3 plus c, simple as that. The memo confirms our answer is correct. Verified using memo. Now let's tackle problem 4, which looks very similar to problem 3. We're integrating 1 over 4x minus 3. As we saw, our function is f of x equals 4x minus 3, and its derivative f prime of x is 4. Let's compare this to our formula. The numerator we need is 4, but our integral only has a 1. How do we make a 1 into a 4 without changing the value of the integral? We can multiply inside the integral by 4 and multiply outside by 1/4. 4 times 1/4 is 1, so we haven't changed anything. We've just rearranged it to fit our pattern. Now we can pull the 1/4 out in front of the integral, leaving us with exactly what we need inside, 4 over 4x minus 3, which is f prime of x over f of. We already know the integral part from problem 3. Let's just substitute that in. So our answer is 1/4 times the natural log of the absolute value of 4x minus 3 plus c. The memo confirms our answer is correct. This technique of adjusting the constant in the numerator is very common when using inspection. Let's look at problem 5. It presents a slightly different arrangement. The problem is the integral of 1 over 3 minus 2x. This again looks like the logarithmic form. Let's identify f of x and its derivative. Our function f of x is the denominator, 3 minus 2x. Its derivative, f prime of x, is negative 2. Just like in the last problem, our numerator is 1, but we need it to be negative 2. We can adjust this using the same method. We can rewrite the integral by multiplying by negative 2 over negative 2. We pull the 1 over negative 2, or negative 1/2, out front. Inside, we are left with the required derivative. Now we have negative 1/2 times the integral of negative 2 over 3 minus 2x, which is the perfect f prime over f form. We can apply our formula. This gives us negative 1/2 times the natural log of the absolute value of 3 minus 2x plus c. The negative coefficient from the derivative adjustment carries through to our final answer. The memo confirms our answer is correct. Verified using memo. Now let's tackle problem 7, which introduces exponential functions. We need to integrate e to the power of 3x. This problem uses another key integration by inspection formula. The formula states that the integral of e to the power of f of x, multiplied by its derivative f prime of x, is simply e to the power of f of x plus c. The logic is straightforward. The derivative of e to the f of x is e to the f of x times f prime of x. So integrating that gives us back the original function. Let's apply this to our problem. We identify f(x) and its derivative. Our function f of x is the exponent, 3x. The derivative of 3x is 3. We need an f prime of x, which is 3, inside the integral, but we only have a 1. Just like before, we adjust the integral. We multiply by 3 inside and 1/3 outside. We can then pull the 1/3 to the front. Now our integral perfectly matches the formula. 1/3 times the integral of e to the f of x times f prime of x. This evaluates to 1/3 times e to the 3x plus c. Once again, we adjusted the constant, found the pattern, and solved the integral in just a few steps. The memo confirms our answer is correct. Verified using memo. Our final problem, number 8, is another example of using standard integrals. We need to integrate the cosecant of 2x. The integral of cosecant is a standard integral you would typically find in a list. The general formula for the integral of cosecant of x is the natural log of the absolute value of cosecant x minus cotangent x. Now we have cosecant of 2x, not cosecant of x. We can apply a similar principle of adjusting for the constant. Think of 2x as our f of x. Its derivative is 2. If we had the integral of cosecant of 2x times 2, the answer would be the natural log of cosecant 2x minus cotangent 2x. Since we don't have the 2, we divide the result by 2, or multiply by 1/2. So, the integral of cosecant of 2x is 1/2 times the natural log of the absolute value of cosecant 2x minus cotangent 2x plus c. The memo confirms our answer is correct. This is a direct application of a standard integral, adjusted for the linear term inside the function. Let's quickly recap what we've learned. We learned that integration by inspection is a powerful shortcut that allows us to integrate functions by recognizing familiar patterns. This method relies on the reverse relationship between differentiation and integration. We explored two main formulas. First, for functions of the form f of x to the n times f prime of x, the integral is f of x to the n plus 1 over n plus 1. Second, for functions of the form f prime of x over f of x, the integral is the natural log of the absolute value of f of x. The key is to look for a function and its derivative. By mastering these patterns and the technique of adjusting constants, you can solve many integrals much more efficiently. This skill is foundational for more advanced integration methods you'll encounter later. Thank you for joining this tutorial from MathZone African Motives. If you found this video helpful, please hit the like button and subscribe for more step-by-step maths tutorials. We'll see you in the next video.